Okay. Let's, since we have, if x is in E instead of discontinuities, I can choose an R of x, a rational number associated with x, that's greater than the limit from below and less than the limit from above. Okay?
Well, we can't see.
So that didn't bother me. F of x below strictly less than a rational number associated with x. Limit from the right. True enough? So do you see, wherever there is a discontinuity, the left and right hand limits exist, and I can always find a rational equivalent. Now, if x1 is strictly less than x2, what we just proved was that f of x1 on the plus side is no greater than f of x2 from the minus side. Which means that R for x1 is going to be less than f of x1 from the plus side, which is no greater than f of x2 from the minus side by this. And then R of x2 is going to be above that. This is the way I pick the R's, right? So now we put subscripts on the x's. The R for x2 is bigger than f of x2 minus. And the R for x1 is smaller than f of x1 from the plus side. Okay, so these two rational numbers cannot be the same, can they? I seem to have, for every point that's a discontinuity point, I seem to be able to put a rational number. What's that mean about the number of discontinuities? It means that they are not greater in cardinality than the set of the rationals, which we know are common. So monotone functions can have removable or jump discontinuities and no more than countably many of them. That's the theorem. I'm always amazed by that theorem because it seems like you start out with such a weak condition. Just monotonicity gives all that. It puts a cardinality constraint and also tells you the type of discontinuity. It's one of those counterintuitive things. It just doesn't seem like there's enough there. And you do it all with soups and ins. That's also kind of interesting. I'll write that up if you want, so that you can. Burke mentions that. So is a monotone function automatically then Riemann integrable? That's a yes. Well, if you have jump type discontinuities or removables at a countable number of places, then so the difference of two monotone functions should be weakly monotone functions, and how badly, I mean, if you have an arbitrary function, this is something that is done in the debate that I give you this one time. If you have a function that's going up and coming down and going back up again, you can just take the up parts and the down parts and decompose it into two pieces. And then flip the down parts. So
so it has this jump discontinuity between it.
Well, Well, no, here's what I would do is like F up would be, I'd be going up like this, then I'd go constant, and then I'd start to go up again. And F minus would be what I need to take away, from this. But then I would flip that. So if I can integrate both of those two functions, then I can integrate the difference, and suddenly I'm integrating the whole thing. This gets into the theory of bounded variation, which we'll talk about briefly. It's a way to characterize Riemann integral functions. So what did we learn today? I'm not sure. We proved everything on our list of theorems, right? I think we proved everything on our list. And we are on the verge. We have a criterion for integrability for Riemann that we did last on Tuesday. And we're on the verge of having a criterion for Stieltjes sums. We played around with a few Stieltjes sums. So let's, on Tuesday, put the kibosh on the Riemann Stieltjes integral.